Hello dear friends, welcome to the lecture of real analysis. We are studying series of real numbers. In our last lectures, we have defined convergent series, or when a series is said to be convergent and when it is said to be divergent. And also we have studied some results. In this lecture, we are going to study series of non-negative terms, but we shall quickly revise what we have studied. An infinite series is denoted by this notation sigma an, n takes value 1 to infinity, and this series, or which will be the terms a1 plus a2 up to infinity. And this for this series we will form a sequence of partial sums Sn, where Sn stands for sum of first n numbers, n terms. So that is a1 plus a2 up to an. And if this sequence Sn, as n takes value 1 to infinity, is convergent, then the series summation an, n takes value from 1 to infinity, is also convergent. And if it is, then sigma an is convergent. So this is the definition for convergent series. And similarly, if if this sequence Sn is divergent, we say the series sigma an is divergent. So this is the series, or about convergence of the series sigma an. And next we have seen a result as if the series sigma an is convergent, then limit of its nth term an is 0. So this is the result we have seen, and the equivalent statement for this will be if limit of an is not equal to 0 as n tends to infinity, then the series is divergent. So that is a result we have seen earlier. And further we have studied series of non-negative terms. The meaning is every term of the series is non-negative, then that is the series of non-negative terms. And if generally we may say series of positive terms. And if this is the series summation an is series of non-negative terms or positive terms, then, and if Sn is a sequence of partial sum, then if Sn is bounded, then the series is convergent, then sigma an is convergent. And if Sn is not bounded, then the series is divergent. So this is another result we have studied earlier. And further, so we have studied what is known as a geometric series. And that geometric series is denoted by x power n. N takes value 0 to infinity. Then this series is convergent, converges to 1 upon 1 minus x if 0 is less than x is less than 1. So this is a result, and this series diverges if x is greater than or equal to 1. So this is the result we have seen for geometric series. And one more series we have studied, which is known as harmonic series. And that series is summation 1 by n. N takes value 1 to infinity. This series is divergent. So these are few results that we have studied earlier in earlier 2 lectures, and this is lecture 3rd on series. And in this lecture we shall study again the series of non-negative terms, a theorem about series of non-negative terms, and this is our theorem number 6. So the theorem is, if sigma an is divergent series of positive numbers, then there is a sequence epsilon n takes value 1 to infinity of positive numbers which converge to 0. This sequence converges to 0, for which the series product of sigma n and n takes value 1 to infinity still diverge. Though this is convergent to 0, and the product series of the product sigma n converges, it still diverges. Though this is convergent to 0, the product series of this product diverges. So this is the theorem that we shall prove. The proof of the theorem. We first form this partial sum of this series sigma an, and for that purpose we consider Sn as sum of first n terms, that is a1 plus a2 up to an. This is Sn. And because this series is divergent, this sequence is also divergent. And because this is a series of positive numbers, each term is positive and it is divergent. So therefore this is a non-decreasing sequence. Then Sn, or instead of Sn we can write the sequence as Sk, k takes value 1 to infinity, is divergent. And now because this sequence is divergent for given m belongs to I, positive integer, I means set of integers, positive integers, there is or there exist again another number, the positive integer n belongs to I, such that this that is Sn plus 1 will be greater than 2 times Sn. See this series, this sequence diverges, and by the sequence diverges means it diverges to positive infinity, because the series is of positive numbers, and therefore this sequence is divergent and diverges to infinity, or we can write this sequence diverges to infinity. And because it diverges to infinity, whatever the number fixed number, for a fixed number 2 times Sn plus 1 will be greater than 2 times Sm. The terms become bigger and bigger, and this can be considered as k. So when we say a sequence is diverges to positive infinity, if the sequence there exists n such that Sn is greater than the value k is taken here as 2 times Sn. And now we will consider the series. We shall show that the series we will consider as k takes value 1 to infinity, Sk plus 1 minus Sk divided by Sk plus 1 diverges. This we shall show. And for that purpose we consider now the partial sum we shall consider as k takes value m to n of this Sk plus 1 minus Sk divided by Sk plus 1. We are purposefully considering this series summation Sk plus 1 minus Sk divided by Sk plus 1, and here we have formed, here it is infinite, but here the sum is finite from m to n. So what will be this is again we can write this relation for this k takes value m to n Sk plus 1 minus Sk divided by Sn plus 1. Now what is the relation between these two sums? Here Sn plus 1 is written and here it is Sk plus 1, and certainly n is greater than m, and the series is of positive numbers, therefore this sequence is non-decreasing sequence, or actually it is increasing, and therefore this number is n is greater than m, therefore Sn plus 1 will be greater than Sk plus 1, and that means this denominator is greater, and because the denominator becomes greater, the value will be less than this value. So this, therefore the first expression is greater than or equal to the second, or the reason can be written as, since Sk plus 1 is less than or equal to Sn plus 1. K takes value m to n, and therefore this, if k is n, then this will be equal, both will be equal, or earlier values this is less than, and therefore this is a smaller quantity than the smaller, or at the most equal to this quantity. And further this we shall write now, it is a fix, n plus 1 is fixed, so we can take it as 1 upon s plus Sn plus 1 common outside the sum, and inside the bracket we write this sum. So this is now independent of k, and therefore can be written outside sigma notation, and inside sigma take m as k as m, and the first term will be Sm plus 1 minus Sm, putting k is equal to m. Next put k is equal to m plus 1, and the further will be, I shall write here, plus S m plus 1, that is Sm plus 2 minus k is m plus 1, Sm plus 1, and plus so on, plus, so what will be the last? Last will be k is n, so it is Sn plus 1 minus Sn. Now what is the sum in the bracket? We observe this Sm plus 1 minus Sm plus 1, these two terms cancel, and again this first term gets cancelled in with the next term in each bracket. Similarly this term will be cancelled with the next term in the next bracket, and thus these first written terms will get cancelled, and but the last term, this is the last term, and this will not be cancelled, and this will be cancelled with the earlier term, and from the first bracket this is a remaining term, that is minus Sm, will not be cancelled with any term. So therefore the two terms remaining are, so first terms of these brackets except the last will be cancelled, and again this term will not be cancelled, this will be cancelled with the earlier. So Sn plus 1 minus Sm remains, or that is equal to 1 upon Sn plus 1 into bracket. This is Sn plus 1 minus Sm. So this is this expression is equal to this one, but this sum is greater than or equal to this expression, means this one, and thus we have therefore summation k takes value m to n, and that is Sk plus 1 minus Sk divided by Sk plus 1. This is, the relation is greater than or equal to, this is greater than or equal to, and the last expression is this one, Sn plus 1, I shall write that as this bracket as numerator, minus Sm divided by Sn plus 1. But you see here we have Sn plus 1 is greater than 2 times Sm, and therefore this we can divide both sides by 2 and half of Sn plus 1. So what is the equivalent relation, or we may suppose this as 1, and from this what we will have is half Sn plus 1 will be greater than Sm, and therefore we will replace Sm by half Sn plus 1, and this quantity will be greater, this is greater than or equal to Sn plus 1 minus, and this is this Sm is replaced by, this Sm is replaced by half half Sn plus 1 divided by Sn plus 1. So, we have subtracted, instead of Sm we have subtracted a greater quantity, and therefore, the value of this will be less, and that means the above will be greater. So, because of 1 we can write by 1. This is the relation. And but you see what is this expression. So, this is equal to Sn plus 1 minus half time of Sn plus 1 means half Sn plus 1 divided by Sn plus 1. So, only Sn plus 1 gets cancelled and half remains. 1 minus half is half. So, this is equal to half. And finally, what we have is this partial sum is greater than or equal to half, or therefore, we have this is k takes value m to n of Sn plus Sk plus 1 minus Sk divided by Sk plus 1, and that is greater than or equal to 1 by 2. And thus, what we have obtained is for any m belongs to I, that is positive integer. Thus, for any m belongs to I, there is another positive integer n, such that the series, so this partial sum of the series, that is k takes value 1 to infinity, and here k takes value m to n, that is this is a partial sum, such that the partial sum k takes value m to n of this expression is greater than or equal to half, means does not form a Cauchy sequence. When we shall say this forms a Cauchy sequence, if it is less than or equal to any value epsilon, but it is epsilon is half, then that is greater than or equal to half, and therefore, this does not form the partial sum k takes value m to n of Sk plus 1 minus Sk divided by Sk plus 1 does not form a Cauchy sequence. Because the expression is partial sum is greater than or equal to half, and therefore, if it does not form a Cauchy sequence, it is not convergent, and means the series is not convergent, or the series, this series infinite series k taking value 1 to infinity diverges. So, therefore, the series of this k taking value 1 to infinity Sk plus 1 minus Sk divided by Sk plus 1 is divergent. But you see, this is what is the value of Sk plus 1 minus Sk. Sk plus 1 means sum of first k plus 1 terms, and Sk means sum of first k terms, and therefore, in this subtraction the last term remains. So, see Sk plus 1 is a1 plus up to ak plus 1, and before earlier to this, that the term will be ak, and what will be Sk? Sk will be first k terms, and in this subtraction these terms cancel, and what remains is ak plus 1, or that means, but summation k takes value 1 to infinity Sk plus 1 minus Sk divided by Sk plus 1. This is equal to summation k takes value 1 to infinity ak plus 1, this is ak plus 1 divided by Sk plus 1, or again that can be written as summation k takes value 2 to infinity, and we replace k plus 1 by k, and then k takes value 2 to infinity sk. This can be verified. See, the first term k is 2, that this will be a2 divided by s2. Here also k is 1, k plus 1 will be 2, that is a2 divided by s2. The terms of these two series are exactly the same. We have shifted k from 1 as k from 2 to infinity, and therefore this is decreased, this suffix is decreased by 1, and this is divergent. Therefore is divergent, which is divergent. And now we take this 1 upon sk as epsilon k. Take 1 upon sk is equal to epsilon k, and therefore this series becomes, therefore summation k takes value 2 to infinity ak upon sk becomes summation k takes value, instead of k we can write now n, replacing k by n takes value 2 to infinity an divided by, this will be 1 upon sk is epsilon k, 1 upon sn will be epsilon n, and that can be written as epsilon n into an. Epsilon n is 1 upon sn, replacing k by n. So this series is divergent, where see, this is divergent means taking 1 upon sk as epsilon k, this becomes epsilon n into an, the series is divergent. And whether it is in having infinite terms, and therefore whether n takes value 2 to infinity or 1 to infinity, it will be the same behavior. The series is divergent. So is divergent where epsilon n and epsilon n is equal to 1 upon Sn, and this Sn is diverges to infinity, therefore epsilon n will diverge to 0, diverges, or this converges. If Sn diverges to infinity, 1 upon infinity will converge to 0, converges to 0, and this is what we wanted to prove. Summation n takes value 1 to infinity, epsilon n an diverge, and this series is a sequence, epsilon n is sequence of positive number which converges to 0. So this converges to 0 because this diverges to infinity, and this proves the theorem. So thus we have proved a result of where series epsilon n divergent. So for example, we can consider like this. For example, let summation n takes value 0 to infinity is equal to summation of n square 1 to infinity positive numbers. Suppose an is n square. So obviously this series is divergent, and we can consider the series of positive numbers which is may be taken as epsilon n, and that must converge to 0. Take epsilon n is equal to 1 upon n. Then obviously this converges to 0. Then epsilon n converges to 0 as n tends to infinity. Limit of 1 upon n. And now, but what is the product of this? And now what is the summation of epsilon n into a n? N takes value 1 to infinity. So this is summation n takes value 1 to infinity. Epsilon n is 1 upon n and a n is n square. So what is this series? N square upon n means n, summation n. N takes value 1 to infinity is divergent. This diverges. That is the meaning of the theorem. Now here we can take epsilon is n as 1 upon n, or we can also take epsilon n as 1 upon n square. Now if epsilon n is, there must exist such a sequence, and that may not be unique. So if epsilon n is 1 upon n square, then this epsilon n tends to 0 as n tends to infinity. Then what is the summation epsilon n a n for the same a n, for this same a n, n square? So will be 1 upon n square into n square, and this is summation 1. N takes value 1 to infinity. So this also diverges to infinity. 1 plus 1 infinite times, that is infinity. So therefore here epsilon n may be taken as 1 for this series, divergent series. Epsilon n may be taken as 1 upon n, or epsilon n may be taken as 1 upon n square. But if you take epsilon n as 1 upon n cube, then what will be the product of this is 1 upon n. Then that also, summation 1 upon n will also be divergent. And but if you consider epsilon n as 1 upon n power 4, then it will be epsilon n into a n will be 1 upon n square. That will be convergent series. So thus the theorem can be understood by taking this type of examples. Now we will solve a problem of, see, the series 1 plus 1 over 2 factorial, etc. So this is a problem. Show that the series 1 plus 1 upon 2 factorial plus 1 upon 4 factorial plus 1 upon 6 factorial, etc., infinite, converges. So this we shall show, and for this purpose we consider its solution as. Now see, what is Sn we shall form. We have Sn. Sn is equal to sum of first n terms, partial sum it is. So it will be 1 first term, this is second term 1 upon 2 factorial, the third term is 1 upon 4 factorial, and so on. So what will be the last term? So actually this is second, this is third, this is fourth, etc. And in each term we can take 2 common. Then 2 into 1, this is 2 into 2, 2 into 3, etc. But that will be the fourth term. So the last term here will be that is 2 into n minus 1 factorial in bracket, or we can write like this. It is 2 times n minus 1 factorial. Now we can verify this. That is, this is the second term, this is the third term, and third term is we have written 2 into 2, factorial of 2 into 2. What will be the next term? That is fourth term will be 2 into 3 factorial, that is 1 upon 6 factorial, and last will be 2 into n minus 1 factorial. And this Sn now can be written as this is 1 plus Now we can write here as 2 factorial, 4 factorial, etc., and we shall write use a relation like this. We have n factorial or 1 upon n factorial, this relation 1 upon n factorial is 1 upon 2 power n minus 1. What is the relation between these two? So, 1 upon n factorial can be written as 1 into 2, etc. So, 1 into 2 into 3 up to n, and this if you replace each term by 2, that is smaller, then this will be replaced by 1 into 2 into 2 into and so on. The last term is n minus 1 times, because these are n minus 1 terms. Each term is replaced by 2, and this is 2 power n minus 1. But here the denominator is bigger, and therefore the value is less than or equal to 3 is less than 2. 3 is greater than 2, and therefore the denominator is bigger, and whenever the denominator is bigger, the value becomes less, and that means this is equal to 1 upon 2 power n minus 1, and that means this is n factorial. 1 upon n factorial is less than or equal to 1 upon 2 power n minus 1. So, this is less than or equal to 1 upon 2 power n minus 1, and thus therefore using this relation we can write the above. So, therefore Sn will be less than or equal to, we keep this term first as it is 1 plus 1 by 2, 2 factorial we write 1 upon 2 itself, and but here we can write this as 4 factorial, and that is less than or equal to 2 to the power 4 minus 1, here n minus 1, here it is 4, 4 minus 1 it is 3, and so on. The last one will be, it is 1 upon, this is what is in place of n, it is 2 into n minus 1, that is 2n minus 2, and we have to subtract 1 from that, and that is 2 to the power 2n minus 2 minus 1, that is minus 3. So, using this relation we have written Sn is less than or equal to this sum, and again that can be written as, we can take from these terms 1 by 2 common. So, therefore, Sn is less than or equal to 1 plus half, and now this from these expressions terms we can take half common, and in bracket what remains is again 1 plus 1 remains here, and 1 power will be less, 1 upon 2 square. What will be next? 1 upon 2 square square. You see here it is 4 factorial, next will be 3 factorial, that not 3 but 6 factorial, and therefore the next term will be actually plus 1 upon 2 to the power 5 and plus so on. 1 by 6 factorial is less than 1 upon 2 to the power 6 minus 1, that is 5. And if I take 1 half common from these expression, these terms, then in bracket it will be 1 by 2 square, this will be 2 power 4, and that is 2 square square, and last will be plus so on, the last will be 1 upon. Now, we should have to subtract 1 from this power exponent. So, 2n minus 4, and that will be 2 square n minus 2, that is 2n minus 4. You should verify this, that will be 2 to the power 2n minus 4, or that is 2 square to the power n minus 2. And thus, this is a geometric sum, where the first term is 1 and the common ratio is 1 upon 2 square, and we have a formula for this. So, this is equal to 1 plus half, and that formula we can write as, see, using this 1 plus x square up to n terms, means up to n minus 1. So these are n minus 1 and this is 1, yeah, totally n terms, and that is 1 minus x power n divided by 1 minus x, if x is less than 1. So this is the formula we will use here. And what is the value of x here? It is 1 upon 2 square, or that is 1 by 4, and therefore it will be 1 minus x is 1 by 4, 1 by 4 power n divided by 1 minus 1 by 4, or that is equal to 1 plus, this is half, and 1 minus 1 by 4 is 4 minus 1, 3 by 4. So half into 3 by 4, half into 3 by 4, but 3 by 4 is at the denominator, and therefore at numerator it will be 4 upon 3. Reciprocal of this 3 by 4, reciprocal is 4 by 3, and in bracket it remains 1 minus 1 by 4 power n, or this is a product, and that is 2/3, 1 plus 2/3. So Sn is less than or equal to. This relation is Sn is less than or equal to this, and which is equal to this one, means finally we will have Sn is less than or equal to 1 plus 2/3, 1 plus 2/3, and minus this expression, whatever it is, 2/3 into minus 2/3 into 1 upon 4 power n, and therefore this is less than that expression. So or if you take n tends to infinity, this will going to be 0, 1 upon infinity will be 0, and thus Sn is less than, strictly less than 1 plus 1/3, or 1 plus 2/3, 1 plus 2/3 in bracket 1 minus 1 upon 4 power n, that is Sn is strictly less than. So 1 plus 2/3, 1 plus 2/3 minus 2/3 into this. So what is 1 plus 2/3? 3 plus 2, that is 5 by 3, and thus Sn is certainly less than 5 by 3, and what that means, Sn converges, and thus the series, the sequence, thus the sequence of partial sum Sn is bounded. So this happens for all n belongs to I. Each term of this sequence is less than 5 by 3, means this sequence is bounded, and if this sequence of positive terms is bounded, the corresponding series is convergent. That we have proved a theorem of in series of non-negative terms, and hence therefore the given series that this series is convergent, and this completes the solution. So we have proved the series is convergent by taking its sequence of partial sum. We have shown the sequence of partial sum by comparison is bounded above. So Sn is less than or equal to 5 by 3, and if the sequence of partial sum is bounded, the series is convergent. This is by theorem 3 that we have proved in our earlier lecture. So thus we have solved this problem. Earlier we have proved a theorem related to series of non-negative terms. Remaining part we will continue next time. Thank you.